Okay, let's just double check your understanding of that refraction and reflection idea. Actually, we're going to be checking refraction more than anything right here on this checkpoint. And the question is, which of these three drawings, if any, show physically possible refraction, right? So here, this is N 1.4. This N, the refractive index is 1.6. This is 1.6, and this is 1.8. And this is 1.5, and this is 1.6. Okay, first of all, this is a lower number than this one, isn't it? And you'll see that this is bent away from this one. So that actually follows the correct rules, doesn't it? But you'll notice that where it is bent. It is from this line right here, it is bent a certain portion towards this normal. This one right here, however, goes beyond the normal to this other side. That can't exist. That can't happen. And here you've got a lower number. And which way is it bending? It's bending this way? No. It would have to be bent this way. So this is not feasible in something like this. Okay? This is not. You can't get there from that particular. You can't have that type of refraction there. So let's go on to the next practical exercise then. Oh, by the way, on page 992, there's table 331. It gives the index of refraction for many of the common materials. And you'll notice they just can't say glass, because you'll notice how many different types of glass that they have noted in that table. So, exercise number 8, which is problem number 45. Here what you have is the diagram there. That's so that the normal to the refractive surface is vertical to the diagram. The angle of refraction, theta 2, is 90 degrees, and the angle of incidence is given by tan theta 1 L over D, where D is the height of the tank and L is its width, right? So I would have said H for height, right? And W for width, but they wanted to confuse you with the other things that we've had in terms of diameter and impedance before. Be that as it may, theta 1 equals the inverse tangent of L over D equals, oh, what happened here? I didn't read the problem. When a rectangular metal tank is filled to the top with an unknown liquid, the observer O, up here, has eyes level to this top, can just see this corner down here. Okay, that's the degree of peripheral vision. A ray that refracts towards O at the top of the surface is shown here. The height of this is 85.0 centimeters. The width of this is 1.10 meters. What is the index of refraction? Okay, and so it's air here, and you're going through this liquid here. It must be strange because obviously you're not taking into account any of the glass there either. So this is the way in which the problem works out. So the law of refraction equals the refractive index of the first medium, refractive index of the second medium, sine theta 2, sine theta 1, and where we have this theta 1, because it's just equal to this right here, must be equal to that. And this right here is just from the geometric relationships. That's how you solve to get this one first. You can then plug that into this equation so that it ends up being 1.26, right? Okay. So anyway, the whole idea is that the angle of refraction, theta 2, equals 90 degrees, and I think those are all of the key elements there. I skipped ahead to the answer before I really discussed the problem in detail. Let's try another one then. Light is incident at an angle theta 1, right here in this medium N1, at 40.1 degrees on a boundary between two transparent medium. Some of the light travels down through the next three layers, okay, this layer and this layer and this layer, while some is reflected upwards and out and back into the air. So the refractive index of this medium is 1.30. Refractive index here is 1.40. Here it is 1.32. This is 1.45. And this one right here is, of course, the refractive index for air is always 1. So what's the value of theta 5 right here back into air? And what is this angle right here? Oh, they want you to use error of 1.00029. I don't know why they want to have 5 significant figures here when you've only got 3 up here, but we'll accommodate them. So reflected light will have the same angle as the incident angle, 40.1 degrees, which then makes an incident angle 40.1 degrees at this N1, N5 interface, right? Right back up here. So this angle and this angle are the same, and so it's going to be reflected down in this manner. So it's going to be the inverse sine, N1 over N2, sine theta 1. So it's the inverse sine of 1.30 divided by 1.00029 times the sine of that 40.1. Okay? Now, when I worked that out, and I did get 56.8 degrees. The next one, you have several different equations. You have N1 sine theta 1 has to equal N2 sine theta 2 equals N3 sine theta 3 equals N4 sine theta 4, right? This, the angles of refraction and the index of refraction make this the way it needs to be. So in order to get this one right here, since we know the initial angle, right, up here, theta 4 is just going to be the inverse sine of N1. Now you have N4 in the denominator, sine theta 1. So it is 1.30 divided by 1.45, sine of that 40.1. And so that right there gives you 35.3. Okay? So it doesn't matter how many different medium you go through, the relationship is the same. All you have to do is make certain you're using the correct refractive index, and then you will get the correct angle. Total internal reflection. If you've got ray A, which is perpendicular to this interface, part of the light reflects at the interface, and the rest travels through at no change. When you have ray B here, through E, each one of these has a progressively larger angle of incidence, right? And so there's going to be more of it bouncing back this way until you're eventually going to get to a point out here where there is no transmission and only strictly reflection. Okay? If the next index is lower and the incident angle is large enough, the light can be trapped inside, right? For ray E, it is 90 degrees, right? This means that the refractive ray points directly along the interface. Any of these points beyond that are going to not be reflected out there at all, but are going to be down further yet. Okay? So this gives the angle of incidence is called the critical angle. This is the critical angle right here. Any angle larger than that are ones that result in total internal reflection. All the light remains inside the glass. So a point source of light is 80 centimeters below the surface of a body of water. Find the diameter of the circle at the surface through which the light emerges from the water. And this, by the way, problem number 9 was problem 51. And this one right here, number 10, is problem 57. So if you draw a diagram, down below here you've got your point of light right here below this surface right here. And it's going up at an angle. And it's a total height here. And you have the angle right here for which the light is going to spread out. So N1 sine 90 degrees equals N2 sine theta C. In other words, you're determining the critical angle here. Because beyond that point, it's going to be internally reflected. Theta C equals the inverse sine N1 over N2, or the inverse sine of 1 divided by 1.33. And 1.33 is a typical value that people use for a refractive index for just general glass. And so that is 48.8. So that tells you how large of an angle this is going to be. Now what you're going to do is you're going to calculate the height here and the, you're going to calculate this distance right here. You already have the height, and all you need to do now is just calculate this right here from the tangent of this critical angle, right? So 2r is going to be the diameter. All you're going to do right here, this is just going to represent r. So it's going to be 2 times the height times the tangent of this angle right here, which is the same as this angle right here, right? Corresponding angles. So this is 2 times 0.80 meters. Tangent of 48.8 gives 1.828 meters. Okay? That's problem number 57. Problem number, practical exercise 11, which is problem 61, so that light initially in material 1 refracts into material 2 and crosses that material, is then incident at a critical angle on the interface between materials 2 and 3. Okay? So it crosses into here, and when it hits 3, it's at a critical angle, so it's just going to be totally reflected. So the index of refraction here is, this is 1.6, this is 1.4, and this over here is 1.20. So for this to take place, what is this angle right here? What does this need to be for this to be the critical angle here, right? If theta is increased, okay, is there refraction of light into material 3? Okay, so we go through that, and we note that the complement of the angle of refraction in material 2 is the critical angle. So N3 sine 90 degrees equals N2 sine of the critical angle. So this critical angle here is going to be the inverse sine of N3 over N2, or 1.2 divided by 1.4, and taking the inverse sine of that. And that is pretty close to 59 degrees. Refractive angle then, N1 over N2, is equal to 90 degrees minus that. So that's going to be 31 degrees. Okay? So N1 sine theta, N2 sine 90 minus the critical angle gives you this sort of relationship right here for what this angle is going to be right here, right? So that is just the inverse sine of 0.451, or it works out to be 26.8 degrees. Now, if you increase that angle, that decreases the angle which light strikes the second and the third interface. Okay? So it becomes greater than the critical angle. Therefore, some transmission into part 3. Right? So there's going to be some transmission by increasing that angle. And I think we'll stop there and continue on with the next section.